Okay, in the last lecture we stopped it here. Now we are going to start from uh, here, meaning 87, slide number 87, sedimentation. So in few words, if I try to explain the sedimentation, sedimentation is nothing but settling the particles in a bottom of a tank. So it could be, the tank could be rectangular or circular, regardless of the type of the basin. There are four regions it happens, four zones in there. So inlet zone is basically, I'm going to show you a picture and other things, settling zone, outlet zone, and sludge storage. So here is the picture. The water is coming this way. Okay. So this part is called the inlet zone, and the settling zone would be this part. So this part would be settling zone, and this is the outlet zone, and this is the storage zone, meaning the sludge that would be settling. The sludge means the settling particles would be here. So these are the four. So this is one, this is two, this is three, and this is four. Right? Four zones in there. Okay, so we have more explanation of those outlet zone, how it works. Fundamental property of water, that is the velocity of the flowing through this, helps us to settle. So in this case, the velocity, water velocity flowing V Q over AC. Q is the flow rate, and AC is the cross-sectional area of the whatever the tank that we are using in this case. So if you would like to solve a problem, then this is a good problem to solve right now. So to find the weir weight. So let me give you an option in here. If we have a settling basin, water is being settled, then the water has to go out part of it, right? The good water, after the top of the water in there. So in this case, there needs to be some kind of weir. You guys have learned something in fluid mechanics lab, I think, the V-notch weir and other things like that. So this problem will help us to how to calculate the weir length we need. The city of Richmond has a low turbidity raw water, and designing its overflow, we are at a overflow rate of 150 meter cube per meter per day. It fits planned flow rate of 0.5 meter cube per second. How many linear meter of weir required? Weir are nothing but like this. Okay, I'm going to show you some picture. So I'm going to show you some picture how it looks like. So weir length of the flow rate divided by the like say loading rate. The flow rate is volume per unit time, and the loading rate is looks like volume per unit time per unit length. Okay, so sorry, yeah, the loading rate, right? So this could be, yeah. So in this case, because of meter cube will cancel out, and the time will cancel out, will stay only the meter. So in this case, 0.25 meter cube per second, and we convert it into day, and this is 150 meter cube per day per meter, so I become 288. So that means the length of this thing would be 288. It could be circular. If we put circular, then all of those can be counted. So I'll show you a picture so we know how it goes. Sedimentation again, sludge storage zone, we explain a little bit here. So coagulate flocks and other things, how it works, you guys can read those there. Concept, how it is sedimentation happens. Main concept is basically in statics, you guys have learned that if something goes here, so this is the settling velocity, right? That's settling, and this is the flow velocity of the water. Okay, so velocity of the water that's flowing in the tank. So what is going to happen in the physics or in statics, we learned that there will be a um, resultant, right? There will be resultant. So this resultant means it will not go this way or it will not go this way. It's not directly settling. If there is no flow of the water, then it will. But if there is a flow, then it will go here. That means it will settle, but it will go settle somewhere around here. So in this case, if I would like to settle things like that, I have to provide some kind of length. Okay, this is the main concept, and this is called the settling velocity. This is called the flow velocity, and the settling happening thus this way. Certain cases they use a flat plate like that, means material goes stuck over here, then comes down at the bottom. So here is the overflow rate. Overflow rate, which is coming out of the tank or things like that. Volume per unit time divided by surface area. Surface area is nothing but if I have a tank here, like this one, and I cut it here, then if I look it here, it might look like that. So the depth into surface area divided by time into surface area, depth over time, because the liquid velocity. So the liquid velocity is the overflow rate, the rate at which it's coming out. Okay, so ultimately it can be converted into liquid velocity, means h over theta, where theta is the called hydraulic retention time. Before that we said t, but in certain cases you can use a t also here, same as a t, and 8 is the depth of the water, right? Here is another problem to solve to find the overflow flow rate. Water treatment plant, a settling tank has a overflow vertical overflow rate of this one and the depth of 6 feet. So what is the retention time? So V0 equal to uh, the gallon per day per feet square. So we are converting into in feet per day. Okay. The retention time theta equal to h over V0. H is 6 feet divided by 80 feet per day. So ultimately it becomes 0.0748 days or 2 hours. Basically, the 2 hours the materials will be staying into the tank, I mean the water. More concept, vertical overflow rates. If the settling velocity is greater than that, then looks like so would be what one would expect 100% particle removal. If it is less than, then 0%. If it is other way, 50-70%, then again depends on the picture that I showed over here, meaning here, depending on how they are, then definitely it would be settling or there will be no settling. So there are different ways to find how much would be settling in here. So if V0 is at the 70 to 50 to 70% of Vs, then an upflow clarifier. For an upflow clarifier, then a certain amount can be removed. So here is the scenario. This is the like say flowing velocity. These are the like say overflow velocity here. So V0 equal to Q over surface area, whatever the surface area we have, settling in an upflow clarifier. The clarifier could be horizontal. In this case, upflow means water coming from the bottom, settling somewhere in the side, and water is going outside from the top. More concept is the same is to find the settling velocity of the horizontal one. It can be done by Q over surface area. Looks like okay, settling velocity is the Vs in here. So ultimately, these are the one I was trying to show you here before. So in this case here, 50% here is looks like escaping. Some of them are escaping here, different lines, right? So the capturing, if you want to capture, this would be the best option, right? So capturing everything. This is under design. This is well designed. This is, I mean, this is the this one is definitely above the design. It's not an over design. This is under design. So here are more scenarios, right? A is good. B is under design. This is over design, right? Yeah, this will not do the job, or this will do more job. This is will not do the job. This will do the perfect job. Okay, this picture I think I showed you before for different zone. So here are some of the problem for the settling velocity. So P is the particle percent removed is basically 100 times Vs over V0. Vs is the settling velocity, V0 is the overflow rate, the rate at which the water is coming out of the tank in the top. So if let's say V0 equal to 0.2 millimeter per second, what percent would be this case? The settling velocity is 0.15 millimeter per second. So it would be 75% would be removal in this case. So if I use this equation, okay. So this is another problem for different cases. So Vs equal to this, that means settling velocity this, since Vs less than this and Vs for a Vs of 0.1 millimeter per second, some fraction will be removed, only 50%, looks like 50%. So for the 2.2 is equal to 0, then it would be 100%. If settling velocity 1, since it's greater than this, then all this one is also 100%. Okay, determination of Vs, how can you do it? It can be done the settling velocity different way. There are three different types of sedimentation. One is called the discrete settling, means individual particle can settle. Okay. Second one is coagulation flocculent settling. In this case, the type characterized by particle flocculate during the sedimentation because it settles like combination of particles. And third one is the hindered or hindered or zone sedimentation, meaning it looks like if we have a sludge on top of the sludge, then it will help settle more in there, right? This is called hindered settling and things like that. Okay, so here are some of those calculation: type 1 sedimentation, flocculant sediment, lab pilot. We can do Jones sedimentation, we can do jar test, and some of them come from our experience. So in this case, I'm not going to derive it, terminal velocity, how to do it, calculations. Basically, it comes from friction, resistance, drag, and gravitational forces into the water. So here are some of those explanation. I have those in there. I have explained all of those. I think in fluid mechanics, you have used those drag and other things like that. If we do it and do some kind of like say summation of fx fy, then finally ultimately we get a equation like this. So in this case, CD is the drag coefficient. You can follow CD can be expressed by that. So then if we replace the CD value different cases, then the VS value comes out to be like this. So this is the Stokes equation that is applied to only discrete settling. It's not applied to the calculation of flocculation settling or type 2 settling. Okay, the terms explanation are over here. I think there may be an exam problem in the homework that you have to do using these equations and so on. Okay, so the above equation is the Stokes law, but this is used for only discrete settling. Please remember that. Okay, terminal settling velocity for type 2 Stokes equation cannot be used, but we can use the lab data column study. Basically, settling column study are the most important one. Then settling column field with the suspended material analyzed, and I think there is a big study there. You can do different time interval, take the samples and plot it and find the different parameters from there. And the zone sedimentation lab data, type 3 sedimentation, zone sedimentation values can be obtained from the lab. The design overflow V0 is set to be about this time the lab value. So here is the jar test, that how it's done, basically 6 or 7 together. Once they do it, then we plot it, right? We plot it, you remember that we did it, we plot it with the turbidity, then whatever the minimum, we come up with the dose. So, okay. Settling velocity and other things like that. Typical detention time for water's coagulated alum and earth salt can be provided like that. Long rectangular circular, this is the overflow rate, and this is the upflow solids contact. These are the typical overflow rate. So this is the settling tank with radial weirs. So these are the weirs I was talking about, right? And they are saying that once the water goes above this, then it come here. This is flat weirs, simple weirs. We don't. This is not a V-notch or anything like that. I think I may have some V-notch. I think these are V-notch, right? So I can see that much, but this looks like a kind of V-notch. Okay, yeah, this is definitely V-notch. I don't know if the 90 degree or 45 degree, but it looks like these are the V-notch. These are the weir. The problem we solved came out to 288 meter, so it could be like total length of 288 meter. Settling tank design common length to ratio is this. Then the length should not exceed 100 meter or 328 feet. Maximum depth is 5 meters, 16 feet. Okay. Column tests are performed to find the optimum detention time and overflow rate, but in this case, we are not going to do that. Literature also provide values. So here is one table. This shows the overflow rate, the range for different areas, and these are the typical ones that we can use. And this table shows like say different column study with a 4.5 meter depth of the column, and they found 40 things is the optimum, and detention time is 2.7. Okay. So, but they have a different one, the 4.5. You can do different studies depending on how deep your sedimentation tank. Okay, we are going to stop here.